Good morning, ME304. This is Group 1A, and we will be solving question 1 from Homework 6. But before we get into it, I would like to make a peace offering to the class in the form of a meme. And here we have a character from The Office, and he looks to be upset and maybe saddened by the sudden realization that he won't do very well on his final because he didn't study, or maybe because he just didn't remember anything he studied, or maybe the exam he studied for a different exam or something. Who knows? Anyway, here's the problem. We want to find the maximum shear stress in the beam. So the first thing we want to do is solve the reactions on the beam using a free body diagram. Here's the free body diagram. And then if we sum the forces in X, we know that it's going to be 0. If we sum the forces in Y, we're also trying to get 0 here. So if we sum the forces in Y, we have two reactions in Y, so we need to take a moment about C. If we take a moment about C, we get AY is equal to 315. Plug in the other equation, we get CY is equal to 405. And now we can draw a shear diagram to find the maximum shear value. The shear diagram looks like this. There's a negative slope here because we have a negative distributed load from 0 to 4. At 4 feet, we have -5 shear value. Shear is measured in pounds, so we have -5 pounds. And then we get to 6, we add an additional -400 pounds, so then we have a maximum value of 405 pounds. Find the moment of inertia. So we're going to find the neutral axis of the composite section. The neutral axis of the section is to be determined using a reference axis as defined here. And using this formula, y represents the neutral axis of each composite component relative to the reference axis. So considering that information, you will this 2.25 right here represents the neutral axis going through 1A, or A1, sorry. And then you can apply that same idea to the other composite section, and then it's just the sum of the areas. And then you get 1.75. Now we're going to want to use the parallel axis theorem. So one thing that might be left out here is that the moment of inertia of a rectangle is equal to 1/12 bh cubed. And the parallel axis theorem is the moment of inertia of the geometry of the shape plus the area of the shape multiplied by the distance from the centroid of that shape to the axis of which you want to take the moment of inertia about. Okay, so here's our 1/12, and since neither of the moment of inertias, or neither of the centroids are about the neutral axis of the composite section, we're going to have to use the parallel axis theorem for both areas. And so the only thing that's going to be, obviously the areas are different because the lengths are different, but then so also are the distances. So we have 0.5 here, which is from here to here, and we have 0.75, which is from here to here, which is right there. Okay, that was really, really, really easy to understand, I'm sure. Q is an interesting little guy, and basically all that Q is the area from the neutral axis to the point of the composite section where you're trying to take your measurement or determine the shear stress in this case. So we're going to use the bottom portion below the neutral axis. So basically that means that we're only using this little rectangle here. Well, and then our y bar prime is the centroid, or the neutral axis of that area. So we know all that. We can just go through with the calculation, and we get our Q value to be 0.656 inches cubed. But this is not a volume. Not a volume. That is true because Jeff Hansen said that on YouTube. So now we can use the shear formula, and it is Vmax times Q over the moment of inertia times the thickness. Plug everything in, and you get 477 psi. And we want to sketch the shear stress. And then we know that it's going to be max on the neutral axis, and it is. And that's it. I hope you enjoyed.